We'll start with our basics. We covered what was cold. Cold is absolute zero, which is minus 460 degrees Fahrenheit. 0 degrees Kelvin or negative 273 degrees Celsius. Oh, not or. 0 degrees Rankine. Or 0 degrees Rankine. It's not that you have to memorize all these numbers. Just want you to realize that that's where absolute zero is. Minus 4, that's the lowest point. Everything above that is going to be what? Heat. And heat is energy. Anything above that cold mark, that's going to be heat. And then thermodynamics. First law of thermodynamics.
Energy cannot be created or destroyed or transformed.
Transformed from one form to another. You don't have to memorize all that whole line. That's what you're realizing about energy. It's not made, it's not destroyed. It's only converted. Just so you get that concept down. It's very important. Number 2 is pretty important. That still doesn't be word for word. You can put the heat travels from a warmer area or space to a cooler or less heated area or space. Several ways to word that. Or you can simply put heat seeks cold. But if you put heat seeks cold, you got to put the quotations with it. So I know that you know the difference between cold and cold. Heat travels to a cooler location. But what affects the second law of thermodynamics? Big, important side of it. Temperature difference. The difference in the temperature and surface area. That's right. The more surface area I have, then the less temperature difference I need. And then refrigeration. Now, I think this one's pretty important for us to define, even though I believe it's a bit dated. Refrigeration. Moving heat from a place that is unwanted to a place that makes little or no difference. Now, I think this could be worded better if we said moving heat from a place that's unwanted to another place, right? Since we don't just dump it to an unwanted place anymore, we actually can put it in the water or something else. But either way, that's right now as it stands the definition for refrigeration. And since we're going to be refrigeration experts, thermodynamic experts, these are important concepts for us to know. So that's what we're going on with that. Any questions about this? No? All right. I'll move it to the side. Ching. All right, and yesterday we also talked about a very important one, BTU. BTU stands for British Thermal Unit. The amount of heat required to raise 1 pound of water, 1 degree Fahrenheit. And of course, we really would like to call out the American Thermal Unit, but then let's change. Now, we didn't define this yesterday. We talked about it. So today I added a definition up here, which is sensible heat. In simple, it's measured with a thermometer. You can see it change with a thermometer. If you want to define it, it's change in temperature without a change in state. The change in temperature without a change in state. So if the temperature of your water went up 5 degrees, what kind of heat would that be? Sensible. What if I took your water and I dropped the temperature by 20 degrees? What kind of heat would that be? Sensible. Because we're just simply changing temperature. What if I raise the temperature of this room by 10 degrees?
Sensible.
Sensible. Good. Excellent. That's exactly right. That is sensible heat. We can measure it with a thermometer. Anytime there's a degrees connected to that, it's going to be a sensible change. And then below that, I put latent heat. Latent is the Latin word for hidden. So it's actually much better if we just called it hidden heat. But it's called latent heat or hidden heat. And then if you want to define it, what it means to us, we can't be measured. But if you want to define it, it's actually a really good definition. A change of state without a change in temperature. Now, when I drove between my car, I had the AC set at 75, and I drove from Arizona to Nevada. Is that the same thing? I did change state. I didn't change temperature. Is that the same thing? No, not quite. But if I boiled water while doing that, then we'd be good. Change of state without a change in temperature. That is latent heat, hidden heat. And this is really important because the most of what we do in HVAC, the magic happens right there. Does anybody remember how many BTU was from changing from 1 pound of liquid to 1 pound of vapor? 970. It just blows my mind that there's that much heat transfer in water from changing state. It's just amazing. It's absolutely amazing. It's a big deal. And then we have evaporation and boiling. Evaporation and boiling, they are technically different things, but as far as what we're concerned with how they're happening, it's a change of state. So we just put them both together. Every time a substance changes state from a liquid to a vapor, it absorbs heat. And what kind of effect is that? Yes, it is a cooling effect. And what kind of heat is that? Latent heat, because it is changing states. It is latent heat. And then also we added condensing. We didn't write condensing down yesterday, so I've added it on the board. Condensing is every time a substance changes state from a vapor to a liquid, it rejects heat. Some people prefer saying it expels heat. Some people prefer to say it gives up heat. They're all correct. Heat's leaving. And that is what kind of effect? Heating effect, yes. So if I see condensation forming on your glass, what kind of heat is that having? What kind of effect is that having on your glass? It's heating the glass. If in the morning you walk out and you see dew everywhere, what kind of effect is that really?
Well, if you have dogs, it's a different story.
Dogs is a different kind of dew. It's a heating effect. The air is giving up its heat to the grass and whatever else it's on. It's a heating effect. So all these concepts what we've covered yesterday, we just added some definitions, and I'm going to leave them on the board here. So if you don't have time to get through it or write it down, or if it's at a bad angle for some of you guys to see, you're welcome to walk over there during any of the breaks and get that information. And I plan on leaving it. I'm actually going to add a few to that. And the other thing we talked about is the refrigeration cycle. So we're going to I always start with the compressor. And the compressor has two names. What's the other name for it? Vapor pump. And what does that compressor do?
Compresses.
Yes, moves the refrigerant. It moves the refrigerant, it compresses and it moves the refrigerant. And by moving the refrigerant, it is sucking in. It sucks. I'm going to abbreviate LP for low pressure vapor. And what else does it do? Pumps. Pumps out a HP for high pressure vapor. So the compressor sucks low pressure vapor, pumps high pressure vapor. That's what it does. Moves the refrigerant. That refrigerant comes out in a line. What's the name of that line? It is a hot gas line, also known as a discharge line. And the state of refrigerant in that line, it is I'm going to abbreviate HT for high temperature. I'm going to put HP for high pressure, and I'm going to put super heated vapor, just to save some room. As long as you understand what HT, high temperature, and HP, high pressure, we're good. From there, the component we go to next, the condenser. Now let's stop right here just for a second. The condenser, what's the condenser doing?
It rejects heat.
Rejecting heat, yes, exactly right. What is it rejecting heat from?
Gas.
The gas, the refrigerants. It's rejecting the heat out of the refrigerant. What's it doing to the refrigerant?
Cooling it.
It is condensing it, changing it from a vapor to a liquid. Yes, that's exactly what it's doing. So as we leave that condensing coil, what state are we leaving of the refrigerant, leaving that coil?
Liquid.
Yes, it is a warm I'm going to put HP for high pressure, subcooled. Subcooled what? Liquid. It's a warm, high pressure, subcooled liquid. What line is this called?
Liquid line.
Yes. All right, what is our accessory that we really want to have? Yes, that's exactly right. And this is a liquid line filter dryer. Can I put it on a hot gas line?
No.
No, because it's a liquid line filter dryer. It goes on the, what line is that it goes on? Oh, yeah, the liquid line. Because it's a liquid line filter dryer. And on this liquid line filter dryer, there should be an arrow. Which way should that arrow point? Away from the condenser, or we could say towards our next component. And what is our next component? The metering device. So you can either say it points towards the metering device or it points away from the compressor. Either one is correct. What does our symbol look like for our metering device? Yep, little circle with an X in it. And the reason it looks like that is if you picture it this way. I have high pressure built up on this side. And imagine a very, very small hole in the middle. And then on the other side, there was low pressure right here. All right? Give you a little better understanding of why they use that symbol. This device is a metering device. What's the other name for it?
Expansion device.
Yes. Expansion device. What does it do?
Restricts the flow of refrigerant from
Creates
high
back
pressure
pressure.
liquid.
Creates back pressure. That's really good. That's what it does. I didn't use that word, but that's just true. That's what it does. Restricts or meters the flow of refrigerant. From a high pressure liquid to a, I'm going to put LP for low pressure mixture. And we're going to add to this today. We're not ready yet. So from there, we're low pressure. So I'm going to use blue for low pressure. And then I'm going to go into my next component. What's this next component?
Evaporator.
The evaporator. What's happening in the evaporator? What's the evaporator doing? Absorbing heat. What's happening to the refrigerant in the evaporator?
Oh,
It evaporates, which means it's changing states from a liquid to a vapor. When it changes state from a liquid to vapor, it absorbs heat, which is a cooling effect. The refrigerant here is absorbing heat, but the effect it has on the air is what? Cooling effect. Over here, we're rejecting heat out of the refrigerant. What effect does it have on the air? It's a heating effect, yes. So we're taking the heat out of the air here, and I'm dumping heat into the air here. Air-to-air heat exchange. Good. Now this line right here, the name of this line? Or?
Gas line.
So to make it simple, I'm just going to write suction gas line. State of refrigerant in this line.
Low temp.
LT for low temperature.
Low pressure.
LP for low pressure. Good. Super heated vapor. Which line's smaller, this line or this line?
bottom.
The bottom.
Good. This one is the bigger line. This line is the smaller line. So far, so good? Any questions? It's pretty much everything we covered yesterday, isn't it? Without the examples?
How
Yes.
fast does this, like,
Oh, gosh, I used to know that. It's quick. It's like it's less than a minute. It's I think it's not how long your lines are, but the refrigerant's flowing. I can't remember exactly. It's 700 feet per minute. I think is how fast the refrigerant's flowing.
okay.
So it's flowing fast. Yeah, it's booking it. It is wasting no time. Yep. Good question. What else? What other questions you got? David, you need somebody? Looking for somebody? Yeah. Oh. So our whole entire refrigeration cycle, everything is happening, all the size is happening right here. I've condensed some of it down to save some room, so we add stuff today. So far, so good? All right. Let's go to a little bit of theory first. We're going to do some lab stuff today, but